All right, welcome to paired sampling. This is two sample means. I'm Bo Corkins, and this is statistics. So, the last concept in two samples is uh, doing paired or dependent means. So, the best way to do this is let's look at an example. Only about 1% of people are truly ambidextrous. All right. The vast majority of us have a dominant hand. All right. So, how unbalanced is your dexterity? The functional dexterity test, or the FDT, measures the time it takes to place a series of cylinders into a set of holes. Researchers measured the time it took 93 children aged 5 to 18 to complete the task using one hand. We have converted these values to speeds. We can then ask, how much faster is the dominant hand on average? So a couple of notes here. First thing, let's talk about the basic one of speed versus time. And I know it seems like a crazy easy idea, but velocity, all right, can be written as an inverted relationship to time. A high time means things are slow, right? We know that a high speed means you're fast, okay? But you want a small time, that means you're fast as well. And I see that like people mess that up all the time because they're like, oh, we always want the bigger number, right? So I want a large time. Well, none of it's time to complete a task, which it usually is. You don't want it to take you don't want it to take you 5 hours to complete a task and someone else it took half an hour. So just be aware of that one. Okay. The other thing, notice how this is worded. We really only have one sample of 93 children. We then measured each hand on them. That means this is paired data. It is purely connected. And with humans, it tends to be like this: hearing in one ear versus the other, hearing, seeing in with one eye instead of the other. All right. Tasks completed with one hand instead of the other. These are things that are paired, they are dependent. Okay. And so that's the difference of what we were looking at before with independent, two separate samples of means. This is I actually only have one sample, but I collected multiple pieces of objects on them. The calculations are actually all occur from the pairwise differences then. So it's actually the differences, and then we have this whole set of data is actually what's analyzed. All right, it's not the two independent, it's the difference of them. Good news, the conditions should look very, very similar. The nearly normal condition, all right, but it's the nearly normal condition on the pairwise differences. The large enough condition, all right, on the single sample. There's only one sample here. So people get confused here because it looks like there's two samples, but you actually only took one sample and collected multiple pieces from that sample. And then be aware that we have this quote paired data condition, but this condition, it's not a real condition. It's really just to help you think, all right, is the data paired? Is the data dependent? Is the data related? Okay. And and now, ideally, all data is going to be related when we're comparing groups. But when we say related, it means it doesn't satisfy that independent groups condition. Because if I have someone, all right, and I recorded their left hand and their right hand, those are going to be connected in some regard. Okay. I could be slower with both hands. I could be faster with both hands. But there's no way that the connectivity between my two hands is completely unrelated. Otherwise, everything should look super familiar. And actually, all this should look much more familiar to one sample means than it does to actually two sample means. Specifically, notice the hypotheses. Mu of the differences, mu d is mu difference, all right, equals 0. And it's always actually comparing a singular value. When we write the hypotheses, we tend to write them individually, but it's actually way more related to one sample means than this is two sample means. In both for both the hypothesis test and the confidence interval. To that end, you can do this in stats t-stats paired, or you can do it with the one sample. All right, stats t-stats one sample, assuming you have the pairwise differences. If you don't have those and you have two columns of data, then you need to do it with this option. Let's go back to our dexterity example. So the question straight out asks here, how much faster is the dominant hand? Because logically, a person's dominant hand, the reason it is titled that is the dominant hand would be faster. If it is faster, that means it has a higher speed, and that means most likely this is sample one. All right, so mu of the difference, which from here on out we title as mu d. This is always going to be 1 minus 2. Okay, so I can write this as mu1 minus mu2, all right, since we identified the larger number as the dominant. And I can write this contextually as mu of the dominant minus mu of the non-dominant, right? Not dominant. So getting the notation, getting all this set up, this little piece right here, that's the most like critical thinking part of the problem and the part that people struggle with the most. Getting this set up so it makes sense. Then we can write out our hypotheses. Now, we start as we did before. Both means are equal. Mu of the dominant, speed of the dominant hand is equal to speed of the non-dominant hand. Then we just have to identify what is the alternative. Since we're identifying faster, again, we already identified what faster means. A faster speed means a higher speed. So that means the average speed of the dominant hand is greater than the average speed of the non-dominant hand. Then for StatCrunch, mu1 minus mu2, bring those to the same side. That means that gives mu1 minus mu2 greater than 0. All right. And then, given that we identified mu d equals mu1 minus mu2, I can then turn this into, okay, hold on, let's write this out one more step. Then let mu d equal mu1 minus mu2. This is the StatCrunch output. So you need to understand what it means contextually, because this is how we're going to interpret it. But you also have to understand what StatCrunch presents and to make sure that your hypotheses are set up correctly. I know both of these cases a lot of the cases we looked at ended up being greater than. That's not always true, right? Could be less than, could be not equal to. So just make sure that you are setting these up correctly. Conditions. Nearly normal condition. We need to take a look at the data. All right, so to the data we go. Dexterity data set. And notice there's lots of info here. Which hand is dominant, the gender, age, all right? And I have the speeds, dominant hand, non-dominant, and the differences. So I could do this, all right, with one sample, but since we know how to do that, stat, t-stats, paired, okay? Paired or dependent, all right? They're basically they mean the same thing. Sample 1 we identified as the dominant hand, sample 2, the non-dominant hand. Our alternative hypothesis should be greater than, and that's the whole thing. That's why we write our hypotheses before you go into StatCrunch. Do not jump into StatCrunch before you've identified a few things. And then I want histogram, QQ plot, and the Shapiro-Wilk normality test. Again, are the same three that we select every time. Histogram. The histogram is unimodal and symmetric. Here's the important part. Notice, there's only one histogram. It's because there's only one sample. Remember, this is 93 children. We collected lots of things on them, right? You saw how many different things we collected. But there's only one sample, which means you should not be saying, oh, it's unimodal symmetric for both samples. No, it is unimodal and symmetric for the pairwise differences. Notice the calculation down here at the bottom, dominant minus non-dominant. That is the difference calculation. Now, again, I could end right there, but I want to keep going just for practice. QQ plot. QQ plot looks just fantastic. Values fall on the line. I do not see an S shape. All right, so Shapiro-Wilk normality test. HO data is normal. HA data is not normal. The p-value is presented to be 0.0479. That means at a 5% significance level, that is below 5%, which means we reject HO at a 5% significance level. And it is reasonable to conclude the data is not normal. That means that condition failed. Now, it's super important to understand this. Notice that we looked at the histogram, we looked at QQ plot, they both look great. But the Shapiro-Wilk p-value said the data is not normal. This was the initial warning I gave with the Shapiro-Wilk normality test. It is sensitive to large data sets. The data set here is 93 values. Its strength is small data sets. Actually, the larger the data set gets, the more likely it is to say the data is not normal because it doesn't perfectly align, all right, with the 68, 95, 99, 7 rule. Approximate symmetry is all we're looking for. But that's why the order in which we test, we verify our conditions, and that's why, right, large enough is at the bottom, okay? Because ideally, you have met it, all right, in an earlier stage. Yes, the Shapiro-Wilk says it's not normal, but it doesn't matter because these above conditions were met. That's why we start with the histogram. if you're not sure on the histogram, use the QQ plot. If you're still not sure, then use the Shapiro-Wilk. Okay. If all three of those failed, then you do use the large enough condition. But ideally, you should have a pretty good answer prior to that. All right, so at least one condition is met. So at least one condition is met. We may assume the sampling distribution of X bar D, the sample mean of the differences, or D bar, all right, you see both notations, is normal. Again, there's only one sample. I cannot emphasize that part enough. All right, calculations. All right, T statistic is 3.97 and a p-value of 0. Hmm, 0.05. It is a greater than, which means it's shaded to the right. All right. And the 0.05 there that I'm writing down is the mean, 0.0542. Okay. Not to be confused, and actually 0.0542. Let's just put that. Not to be confused with significance level of 5%. So p-value is small, reject HO at a 5% significance level. So there is strong evidence to show, important part, again, when you interpret, this is what you should be interpreting. This notation is good, but that's what StatCrunch output is. Mu D equals 0. The average of the differences equals 0, or the average of the differences is greater than 0. That actually doesn't have any interpretation. This up here does. The average of the dominant hand is greater than the average of the non-dominant hand. That we can actually interpret. And so that's what we want to make sure that we are focusing upon as well. Okay. So there is strong evidence, all right, to show that the true average dexterity of the dominant hand as measured by the FDT, the functional dexterity test, all right, is greater than the true average. Show that the true average dexterity speed, let's say dexterity speed is what it is. The true average dexterity speed of the dominant hand as measured by the FDT is greater than the true average dexterity speed of the non-dominant hand as measured by the FDT among 5 to 18-year-olds. All right, right? So the true average dexterity speed of the dominant hand as measured by the FDT is greater than the true average dexterity speed, right, of the non-dominant hand, right? Mu D, mu dom greater than mu non-dom. All right, last little thoughts here. So the toughest part is actually identifying paired data versus independent data. Independent means that we looked at last time versus the paired or dependent means that we looked at this time. The biggest thing is you just have to look at the data, all right? And it's usually about people, right? Are the same people or animals conducting this same task? If it is, right, are the same things doing two different things? If it is two separate groups, that's this top case. That's independent. Okay. Now, without a doubt, if the sample sizes are different, that's a dead giveaway. But if the sample sizes are the same, then you need to determine whether you're dealing with dependent or independent data. And that's the stuff that you need to really focus upon. So what can go wrong? Without a doubt, the biggest thing that can go wrong, failure of your conditions. Check that nearly normal condition time and time again. All right. And watch out. Independent versus paired data. That's a tough one every time. Because they're both means, they both appear to be two sample means, but only one of them is actually two separate samples. One is the same sample with multiple pieces of information collected. All right. We will end it right there for the day. Thank you very much and have yourself a great day.